All right, good afternoon. I've moved over here so I don't feel like I'm leaving out this half of the class. Plus, I got to sit down because it's the only way I can do this. So we'll see if this works. When I'm over there, I feel like the Wizard of Oz, the guy behind the curtain or something. But anyway, hopefully things are going well. I believe most of you should be at a place where you're going to be running up to the deadline of the 2 weeks of free access. So you do need to pay for the access through the website. Click on the button, or else you will lose access to it. I think you can then go through a process to get back, but better to pay before you lose it. Um, you and they may ask for your address, but that's usually for your credit card, so it's still just an ebook. They're not necessarily in. I think there's two options. You can get an 18-week or a longer one. So that's like 70. I was seeing someone had $77 for the basically one semester access, which is plenty. Um, anyway, if you got questions, let me know. The other thing I noticed is I was talking about the due dates, and I had changed them to September 1st, but I realized I was doing it on the master section of the course, which that's what everyone copies their stuff from. So hopefully they were all copied, and I didn't mess up somebody else's due dates. So I did yesterday update the due dates to September 1st, which is Friday for the first three that we have. However, what will I be doing on Friday morning? Did I tell you guys? Maybe I told the other class. Friday morning, I will be extending those to the date of the test, so that, again, hopefully you've at least started it and got it, but sometimes there's one or two questions that are just not clicking. It's better to move on, and then sometimes as you move on, you'll come back and then it will click. So I'll make sure you still have access to work through the homeworks, but I have these due dates to kind of, if you're like me, you kind of, if there's no due date, then I'll just wait till the last day. So you should be spreading it out. So anyway, those due dates will move. The other thing I will do on Friday is I will update the grades in Canvas, because that's a manual process. I have to copy them over from WebAssign, put them in a spreadsheet, move them over. So I will do that update. It is not a final update. I will update again on Fridays, and then I will update again after the test. So don't worry that, I've only got halfway done and I'm still working it. That's okay. We'll get the updates. So it's just sort of a snapshot of where you're at. And now if you say have 70% and then it shows up as 0, do contact me, because then that means there's something in the transfer process, because it takes me sometimes an hour, especially the first time, to get it set up. But again, don't worry, as long as it matches what's in WebAssign, because it will get updated. Okay. The other thing I wanted to update you on is the ebook. I haven't really introduced it, and I'll be honest, I really didn't look at it except for about a year ago when I started teaching this. But they have updated it, and I'm going to introduce you to a couple features that are here that might be helpful. Because some of you have said you get into homework, and some of the questions you only have one attempt and you don't quite know. The textbook actually has some practice examples in there, and there's in the homework you can actually see a question, click on an answer, so you can get an idea of what's going on. So I'm going to show you, so this is the textbook. Notice we start in chapter 10. I think the next class actually goes back to the earlier parts of the textbook. They use, or at least they used to use the same textbook. So I'm going to go, we just did 10.5, so I'm going to show you a few things that are in here. And again, okay, there we go. You'll see that it looks like some of the slides I've been doing, because I use their slide deck, and they just take snapshots of some of the textbook. There's some quick examples, but what's kind of cool here, which I didn't realize at first, that on some they have these your turn where you can actually input things. So this is, we were talking about a point and plus h. You can actually change what the value of h is in here. So it's at 1 right now, and I can do 0.1 and then calculate, and notice yeah, I guess you can kind of, it's changing the slope here. And I can do 0.01 and calculate, and it's 8.02 and so forth, and then it's also, okay, so the derivative at 3 or the slope at 3 must be 8, and it's using the slope formula. Okay, and then you can check your answer. And this is in the textbook part. It's not the homework part. It's just, so it's somewhat of it's interactive textbook. Okay, so there's these parts, and as we go forward, you may find some of these to be helpful. There's, again, it's like a textbook. It's got pictures. It's got some other examples that might be helpful. Here's another interactive. Basically on this one, you would use your graphing calculator to come up with these values. I didn't quite like it as much as some of the other stuff in here, but there was one here on tangent lines, because I've had a few questions on tangent lines. Here you can actually zoom in. Let's see. Oh, you have to move it up sometimes, but you can zoom in by a step, and so you can see that as you zoom in, you get that local linearity we were talking about. And then there's this one where you can actually make h smaller, and it shows it getting smaller. Yeah, maybe make it bigger. Okay, so, and then it shows it going from a secant line to a tangent line. And then there was one in here that just showed how the tangent line moves. Let's see if I can find that one. The other thing to watch out for, though, is there's going to be stuff in the textbook that we don't talk about in the lecture, and that means it's not in our homework, because we've just chosen some of them. So, like, we don't get too much into the notation part. Let's see, is it this one? No, this. Anyway, if you look around, you'll probably find it. I think there was a graph in here that had the tangent line on it. They do show some of these, what the graph of the derivative would look like, because there's a couple questions like that. So it'll give you some additional stuff to take a look at, try for no penalty type thing. And as you get into the homework, they actually provide answers for the odd numbered questions. So you might see a similar homework problem that we've got assigned to you. They've got various ones in here. So you might come in here and look at this one first and say, okay, this is what's going on. So you can kind of go, instead of having to go to the back of the book like in a physical book to look up the answer, you just click on a button, it'll give you the answer. So sometimes, if again, you could find a similar problem to the homework, because that's where they're getting the homework problems, and just kind of see what are they even looking for. There was one in I can't remember what section, but the data was in millions of dollars and the answer was in dollars, and so that was, everyone pretty much had the right answer, but because of the unit change, you had to multiply it by a million to get the right answer. So going through the homework, you might have picked up on that. I would have picked up on. I got it wrong 3 times myself before I could figure it out. So those are there, and again, you can just kind of, once you get into a chapter, you can go to any part of it, and if you want to get back to the textbook, just click on the X, and like today we're getting into chapter 11. I don't think there's as much interactive stuff that you're going to need, but again, you might come here to some of the homework problems and just, here's the question, there's the answer, and kind of start seeing a few things. And in the text itself, it gives you some chance to try things and put it in there, again, for no penalty at all, so that you can pick up the techniques. So I just wanted to let you know it's not just information, it's actually got interactive stuff that can help you learn the material. Okay, so, and you all have access to that ebook. Any questions on that part? All right. Okay, so we're going to get into 11.1, which are the shortcuts. So we've been sort of dancing around what is a derivative. It's the slope of the tangent line is really all we've been able to tell you so far. But we've seen that if you take a graph and you could actually graph its derivative, so you get a new graph of that derivative, which means the derivative itself must also be a function, and it is. So we've talked about the derivative being the slope of the tangent line at a point, but it's at every point, and so if we get the input is the x value, the output is the slope of the tangent line, that's a new function, and that's what today's going to be about, finding out. So we'll go here. So these are going to be our first techniques of finding a derivative. Now, we didn't go through all the algebraic manipulations. If you go into the textbook, in the previous chapters, you'll see they spent more times on something called the difference quotient. And that was that formula that we talked about, f of a plus h minus f of a. So it was, that slope formula that where the 2 points became one. We looked at it graphically, we looked at it numerically, but we didn't do it algebraically, because that gets complicated. So we're hoping that we move into this. If you did it algebraically, you could actually derive some of these things we're going to show you today. But one of the things you would derive is this shortcut rule. So this right here says that the calculations of the derivative using limits is just tedious, and nobody likes it. I don't care how much of a mathematician, a macho mathematician you think you are, nobody really likes doing limits again and again and again. Okay, and the other thing is, it takes us away. There's this thing about problem solving. If we can make the techniques to solve that problem smoother, then we can focus on the problem and its solution rather than all the techniques to get there. A lot of times when we're getting, the algebra techniques or the math techniques, we lose track of even what the goal is. So that's where these shortcut rules are going to be very helpful. And this power rule is really the start of it all. What the power rule simply states that if we have a function, and we'll just use this example, the function's x squared, that its derivative, and again, we could do this with that limit as h goes to 0 of that difference quotient. We could actually plug it all in and prove it. But what we find out is what ends up happening is it's as if the exponent comes down and multiplies by the 1 in front, so 1 times 2 is 2, and then we just subtract 1 from the exponent, and so we've got 2x to the 1, that is its derivative. And it is. If we look at these two and you'd use all the techniques we do to find the derivative of the first function at some point, you'll see that you could have just plugged the x value into this function, 2x, and you would have gotten it. Okay, so we know, one of the things we do know is that hopefully with x squared, I'll just kind of show you, remember it's a parabola, at 0, the slope, since that's the vertex, someone I think noticed this, is that when you've got a vertex, the slope of the tangent line is always 0 because you get a horizontal tangent line. So the same thing happens if we take its derivative. If we look at its derivative at 0, we see, yes, indeed, the slope is 0. So when we see this notation with this little prime, remember what we're getting is we're getting a slope of a tangent line. We're getting a rate of change. We are not getting a function value, right? If we plug in f of 0, we get 0. Okay, so that's one place where actually the function value and the slopes are the same, but we go to different points and it could be different. Okay, so function value gives us a value, and again, it might be a profit, it might be a cost in a business setting. But remember, whenever we're taking a derivative function, that derivative is giving us a rate of change, how the profit is changing, how the cost is changing, not what it is, but how it's changing. Okay, so those are the two things to kind of keep track of. But we'll get back to the story that we're really looking at, is how do we take the derivative? Again, the power rule is just take the power, move it down in front, multiply by that power. And so this is 3 times 1. Then subtract 1 from the exponent. We're going to see that it'll give us a rule on this. So yes, this is just x to the third becomes 3x squared. That's its derivative. Okay? That's all there is to taking the derivative. A lot easier than using limits, right? And using this funky slope formula where we had to subtract 2 things in the top, subtract in the bottom, and then divide, and then maybe use a limit. And oh man, that was... Oh, here it is. So here's the rule. If we have any power type function, x to some, any power, and it doesn't even have to be 1, 2, 3, 4. We're going to see it works with negative exponents, it works with fractional exponents, anything. We just take whatever that exponent is, put it in front. We're actually multiplying, so we'll see there's a special rule for that, but in this case we're starting that there's a coefficient of 1. So we multiply in front and then we subtract 1 from the exponent. Simple as that. That's all there is to it. We will now be able to take every derivative. And then we can graph it separately. We can analyze it separately. We can plug in x values and get them. We don't have to use this cumbersome slope formula anymore. Because when we have the derivative, what else do we have in terms of the tangent line? We have the slope of the tangent line. Okay. And remember that tangent line, whenever we've got a function, that tangent line is sort of where we would go if we sort of lost all constraints. So think about it, if you were driving along a curve and you hit some ice, friction keeps you on the road. When you lose your friction, you go in the direction you were going. I had it happen to me. Fortunately, I was going straight, so I just ended up going straight down the highway. I wasn't on a curve. If I was on a curve, I probably wouldn't be here today. So the black ice is no fun. Okay, so that's what that tangent line is. So remember, the derivative is always giving us the slope of the tangent line the function is giving us the function value at that point. Okay, and you'll get to it. So again, they just give this example, which we've already done. I don't know why they give the same example twice, but here's x squared. To take its derivative, bring down the 2, subtract 1, and we've got its derivative. Okay, and if you've got this part, the rest of it is pretty straightforward. We're going to see a couple more rules, but they're sort of intuitive, right? We'll see. So here's where it gets a little dicey, is how about 1 over x? Where's the exponent? But that doesn't seem to fit that rule, right? X to the n. How could we get this 1 over x to fit the rule, to look like the rule is x to some power?
Isn't it a negative exponent?
Excellent, yes. So some of you will get to the place where you'll just look at it and you'll know what to do, but I always have to kind of go to this route. It's really x to the minus 1, so it's the reciprocal. But now that it's x to some power, right, we do exactly the same thing. So what we're going to do is we take the exponent, it's going to come down in front and multiply. So we're going to get a minus 1x. We're going to subtract 1 from the exponent. This is where sometimes negative 1 minus 1 is not 0, it's negative 2. So when we have negative exponents, we're subtracting 1. The exponent sort of seems to get bigger, at least bigger in value, right? It's negative 1, now it's negative 2. That's all there is to it. You might just see it as negative x to the negative 2. Sometimes they like to have answers written with positive exponents, so then we return it to being a positive exponent. So we would write this as negative 1 over x squared. Okay, so that's, again, it's not all simple, but you have to remember some of these algebra rules. If we've got something in the denominator, we make it a negative exponent, do our work with it, and then return it to a positive exponent sometime. So b is really the same thing, right? Which should we have with b? X to negative 2, right? So that's And again, some of you will just be able to look at it and you'll get it. But when I do it, I typically would take like 2 minus 1 and I'll put negative 1 power. But it's right when we got it here, when I subtract 1, I'm going to get negative 3. So we just have to make sure we get everything right. So the negative 2 comes down in front. So I'm going to put a little marker here. We'll get to this in a moment. It's just kind of a derivative with respect to x. So I'll formalize this, but this is another symbol we use for the derivative, and you'll see your graphing calculator has that in there as well. So I'm taking the derivative with respect to x. So what is that? That would be negative 2 x to the negative 3. Okay, so subtracting 1 from the exponent. Again, sometimes it's a perfectly fine answer. However, sometimes they want to have the answer with positive exponents. So if the instructions say write the answer with positive exponents, it's going to mark this wrong. Doesn't mean it's wrong, but it just means it wants this. Okay, so we're going to get comfortable with moving negative exponents up and down, or taking fractions and making them into negative exponents. It's just one of the things we need to be able to do. So far, we good? Okay. Next one. Again, a little challenge, but if we think back to our algebra, we hopefully should have it. So what type of an exponent does a square root imply? It's a fractional exponent. This is really x to the 1/2. They are exactly the same thing, a radical or a 1/2. We could do either way. Radicals were easier to do when they were doing printing than to do a fractional exponent, because they didn't have little stamps that did that or something. So that's why we've got the radical. We might not have ever needed it if we had all the technology we have, but anyway, so if we have this function and we want to take its derivative, what do? The exponent comes down, so what are we multiplying in front? 1/2. It just is what it is. And then this is where it can be a little confusing. We're going to need to subtract 1 from the exponent, right? So here's a little thing, is because sometimes we're going to have a cube root, which would be 1/3, or a fourth root, which would be 1/4. When you're doing fractions, remember to subtract, you need a common denominator. So I like to just, at the beginning, let's write 1 as 2/2. It's just easier to deal with, right? Instead of writing 1, oh, now I need a common denominator. 1 is also 2/2, it's 3/3, it's 4/4. And this is the one that's going to help us. So 1 minus 2/2, well, 1 minus 2 is negative 1/2. So notice we end up with a negative exponent. And so again, you might want to see this, the text might ask for the answer to be with a positive exponent. It also, sometimes you'll see it will be put back as a radical, and so this is the middle work. And so this is going to be 1/2. Since it's negative, it's going to go back into the denominator, and since it's a 1/2 power, it'll be a square root down in the denominator. And notice this is just 1/2 times it, so it's 1/2 square root of x. Okay, so again, just following that rule, but here we get into, we're going to maybe need to do it with fractions. So this would be the derivative. And again, we've got to remember, tell yourself this is a slope of a tangent line. It's a function that will give me the slope of the tangent line. The other function gives me a value of something. We doing okay so far? Okay, so these are kind of the squirrely parts. It gets easier after this. Here's this other notation that I just threw in, so now we'll talk about it. Is that, and again, they talk a lot. Part of this is in math. Math was really developed in multiple places around the world. Calculus itself, specifically, it was developed by Newton in England, Leibniz in, was he German or was he French? I can't remember. Leibniz. German or French, I can't remember. Anyway, so there was this, it was developed at the same time, at least the version we use here. It was also used thousands of years before that in other cultures as well, with different notations. But so we get two different notations. We've been using this prime, f prime, to represent the derivative, and that's the one I kind of like. It's nice and clean. But then there also the derivative of this with respect to x, they use this sort of notation, derivative with respect to x. We're going to see when we start doing it with functions, we also do this. We're taking sort of the derivative of y because we're thinking of it y as a function, but it's always x is the input variable. So the bottom tells you the input variable. The top will tell you the output variable. And when you don't have any letter at the top, that means it's just taking an expression and say, give me the derivative of this expression. I don't have it's not really a function. Okay, so it's, we'll use this sometimes because the book does, but just sort of notice we can always translate. If you don't like it, which I never did, I always would rewrite the question as this with the prime because I just liked it better. Sometimes I drop the x, so I would just, we got a function f, I've got its derivative. To me, those are nice and clean, and those are the ones I use when I'm doing my work. I don't like this d of dx, but it does come in handy for one of the sections, so we will use it. It's a little easier. But so just note that that function's there, or that those symbols will be there. When you see it in the homework, just be able to translate it, and oh, that's just asking for the derivative. And look at it more as language. There is some technical sides to it, but don't worry about trying to understand it. It's just a symbolic difference in language because of area where it was found. Okay, so again, they take you through it. Here's the derivative with respect to x, x to the third. Notice it's the same thing. The 3 comes down, multiplies, subtract 1 from the exponent. That's all that's going on. Okay. So now we're into where we're going to be able to, so right now we're sort of limited. We can only take it one thing at a time, right? X to the 1 power. But what about if there's multiple things being added or subtracted? Well, the good news is if we have multiple functions, if we're adding or subtracting them, the rule is we just do it term by term. And I'll show you. So the sum rule is just, yes, the derivative of the whole function is the same as taking the derivative of each piece. Okay, so example, if I had 2x to the 5th minus 3x to the 3rd plus 2x squared, those are like 3 pieces of a function. Well, it's one function, right, or something, but I could also look at it as each piece. So what I do is when I want to take this derivative, and I'll use that, is I do it for each individual piece. So it becomes 5 times 2, 10x to the 4th, right? So I took the 5, I multiplied it by the coefficient in front, and subtracted 1. That's all I did. And do it for each of the terms. 3 times negative 3 will give us negative 9 x squared. So I'm subtracting 1. Maybe I'll go up here. Subtract 1. Subtract 1. Subtract 1. Again, remember, bring down the number first, the exponent, so then it's 2 times 2, which is 4. 2 minus 1 is 1, so it's 4x to the first. There's our derivative. We're done. Okay. And it's sort of intuitive. Does it make sense that if I can do it for one, that I can do it for the others? I think it is. Mathematicians don't ever take anything intuitively. They painstakingly will take the time to prove it. I let them do that work, and then I'll just say, okay, you proved it, so now I can use it, and I don't have to do the hard work. Okay, so that's how we do it. And I sort of introduced this. I took 5 times 2 because for me that was sort of intuitive thing to do. If I could take 5 and multiply times 1, wouldn't I just multiply by 2? But again, mathematicians, they make a special rule that if we're multiplying by a number, so here's 2 times x to the 5th. So again, the way they look at it, it's 2 times x to the 5th. So they take the derivative first. So it's 2 times 5 x to the 4th. And then they multiply by the 2. And notice it's the same thing I did. I just go ahead and do it in the front part. So they have a special rule, and sometimes you'll see all of these, but for me, it's intuitive. And sometimes those special rules kind of threw me off because I said, why do we need this? And so, it was actually more confusing to me because to me, it was second nature. Okay, so again, we're just to take the derivative as long as we have x to some power. Now we're going to look at some other rules when we have logarithms, when we have exponentials like 2 to the x. That's all different stuff, but we do with that later. What we're going to work with is just polynomials, something to a power, and it's just take that exponent, bring it down, multiply, subtract 1 from it, and we'll always get the derivative. Okay, and again, just notation, and again, partly because I was a math major, a lot of engineers, I was in engineering at the beginning, or trying to be, and you get into all this, you want to get into understand all the details about the notation, and just say it's like a different language, right? And so this is the same thing as saying, f plus g, let's take its derivative. Well, that means you can take the derivative of f, take the derivative of g, but when we're actually just using it, it's just piece by piece, term by term, we take its derivative, and we'll be fine. For multiplying by a constant, we just take its derivative and then multiply by that constant. Okay, and again, the thing is in math, we don't take anything for granted. We don't make assumptions, or at least they don't when they write it. So they have to prove it out, and so that's why they go through all this logic. But as you see here, they break it down sort of painstakingly. And when I say show your work, I would be perfectly okay if you jump from here to here. You don't have to show all this notation. I mean, maybe in a math class and you're doing proofs and stuff, you have to show that. But for us, we just have to be able to take it. So x squared is, its derivative is 2x. X to the fourth is 4x to the third, and since we're subtracting, we're still subtracting. So it becomes, as you're going to see, you're going to be able to just kind of jump there. Again, it's just take that exponent, multiply whatever's in front, and subtract 1. Again and again and again. So here's another one. This is actually looking easy in comparison to the ones we've already done, right? So think about this. Find its derivative. So go back, use whatever notation you want. Pause for a moment if you want to go ahead and write it down. I'll take a drink of water to slow me down. So we should get what? 6x to the first power. I like to write that first, especially at the beginning, just to recognize that I took 2 minus 1 and I got 1, and you could leave it in. Then I get 2x, and there's no exponent there. Now this is maybe a tricky one. What do I do here? So multiply, I get 2. What happens to the x? 1 minus 1, x to the 0. What's anything to the 0 power? 1. Okay, except for 0 to the 0, that's undefined or indeterminate. But so what we'll see is when we've got something just to the x power, it actually will go away, won't it? It disappears because it's x to the 0, which is 1. 2 times 1 is 2. So in our answer, I guess you could put it in there. There's nothing wrong with it, but you won't even see it. But what about minus 4? We haven't talked about a constant yet. I don't think we have. Goes away. Why?
Because there is no tangent line for it.
If we have a constant, okay, let's think of what a constant. So we'll break it off as if it was separate. So this minus 4 is like a function y equals minus 4. What does the function y equals minus 4 look like? It's a horizontal line. Remember, a line will have the slope the same slope everywhere else, what is the slope of a horizontal line? 0. So it's always 0. So in this case, the derivative of a horizontal line is always 0. So you're right, it does go away, but it goes away because it's 0. And because a constant is really a horizontal line. If we look at it, so this is where it's helpful to look at it as pieces. But again, you could also remember it just goes away. But again, these last two terms, these are sometimes the hardest part. People will forget that derivative of a constant is 0. They'll leave it there. Yes?
So the y always goes away, like in every case?
Well, not the y, but a constant, so a number. So if you have a number there, so actually I broke this down thinking of it as 3 different equations, 3 different functions, and then I also thought of it as y equals 2x. So notice the first ones, there is a derivative that comes here, but when I have it just equal to a number, you're right, it will always be 0, so it just disappears. Okay, good. Does that make sense? Sort of. And again, you'll get some practice with this, but just to, as you're doing things, it's always best to kind of see where you're at and what you're feeling, and recognize things that are maybe a little bit more difficult to you. And don't put yourself down because I don't really understand why this is 0, but I can do it. But yeah, there's been things in math that I just did because that was the rule, but I'd be honest, I don't really understand why. Yes.
Can you show how you solve the second part again? It's just one.
Which part?
So, how did you just get like +2?
Oh, +2. Okay. So good. So again, this is oftentimes the hardest one of them all, is what is 2x to the 1 power. So 1 will come down and multiply by 2. So I'll think of that as 2 times 1. But then I've got x to the 1 minus 1. So technically what I have is I have 2x to the 0 power. And when I have, I don't know if it would help, but 4 I could write as 4x to the 0 power. You could write anything as x to the 0 power because x to the 0 power is 1. Okay. And when we multiply by 1, it doesn't change. So this really just becomes 2 times 1. And so it goes away. But again, that's one that even to this day, I can do it, but I tell you, in my gut, it doesn't feel quite right. So I even have, it's like, why does it just go away? Okay, I know the logic behind it, but it just doesn't, some of these rules just don't seem to work. But does that help? Okay. And again, there's a plus, you could put a +0 but the derivative of a constant is always going to be 0 because a constant is a horizontal line. Good so far? We don't have too much more to do today. We got plenty of time. Again, we'll have some time. As we go, we'll try to break it down so that we can get sort of the concepts, and then 15, 20, 30 minutes maybe, if you want to stay and work on some things and ask some questions, that'll be good. Okay, this one looks kind of gnarly, doesn't it? So this one, we want to take its derivative, right? And again, you could kind of do it piece by piece, which is kind of the way we're going to do it, and then we put it back together. So this first one is 2/3 x to the first power. So that's what I'm going to do, is I'm going to rewrite this so that every one is x to some power. And even x to the first power, I'm going to write that as x to the first power, so there's just not x to nothing, right? Because it's, how about this 6/x? How am I going to rewrite that? X to the -1 power. Okay, so just, this is one practice. You're kind of going to you're going to have a number times x to some power, and then I can I can apply the power rule for each one of these. This one here in the middle, right? I've got a 2/3. The 3 stays down there. This is a hard part because I can see the exponent is going to come up and I'm going to make that negative, but the 3 is a number. It's going to stay in the denominator. So I've got 2/3 here. And then I'm going to have x to the -0.2 power. Okay, so notice when I take an exponent that's in the denominator, when I move it up, it becomes a negative exponent. We okay with that? Not really, but we'll get there, right? Practice, practice. Okay. And then I've got this last one, and I'm going to rewrite that as minus 1/2, so taking the number, moving it in front, x to the 4th. So all I've done is algebra to rewrite everything so it's x to a power, something times x to a power. And then to take its derivative, oops, I'm sorry, I haven't taken its derivative yet, so I shouldn't say I'm taking the derivative. I've just rewritten the function. Now I'm going to take its derivative. Oops. Now I'll take the derivative. So the first one, and I'm going to write here, I still have to upgrade my license so I can have color because it's helpful. I'm sorry about that. But so I take the 1 and I multiply. So what's 2/3 times 1? 2/3. I love to multiply by 1. I can do it all day long, and I usually get it right. It's a joke, but I was pretty proud when I told my dad in like 2nd grade, I can really multiply by 1, Dad. Give me any number, I can multiply by 1. He wasn't impressed, but I was. And then we're going to subtract 1 from the exponent, right? 1 minus 1 is 0. I'm going to write it down here, x to the 0, but that's going to disappear when we do our final answer. But I like to put it there to just to show what I did. You don't have to, but you could just have it gone. Second one, I've got -1 as my exponent. So when I multiply it times -6, what am I going to get? +6. So this is, again, another one of my places where I can make mistakes all day long is with negatives and getting them mixed up somehow. Okay. Then I'm going to subtract 1 from the exponent. Be careful if you're doing this all mentally. Sometimes you'll put 0 there, right? Because you'll do it's -1 minus 1. That's a -2. So the hardest part of calculus is really not this rule of taking the derivative. It's all the algebra, all the arithmetic that we have to do behind the scenes. So far we're doing good? Okay. Next one, we've got this funky exponent. It's a fractional. You could write it as 2/10, I suppose, if you wanted, or 1/5, but 0.2 is perfectly fine exponent. We're going to multiply, so it's negative. So I better do this now. Negative times a positive is negative, right? And then we get 2/3 times 0.2. I'm just going to, sometimes I like to just get everything done. I'm just going to put it in, and I'll multiply it later. Okay, but that's showing what happened. And then it's going to be x to the, remember I'm going to subtract 1. So what's -0.2 minus 1? -1.2. Because they're the same sign, so you add them. You actually add them. So, and then we're going to put them back down in the denominator. And then this last one, I've got 4 as my exponent. 4 times 1/2. Might do this a little. So 4 times 1/2 is like 4 divided by 2. The answer is going to be 2, right? So I'm going to clean this one up a little bit. I'm going to go -2. What's my exponent? 3. Just remember to, there's 2 parts to it. The other thing is, as we're doing this, I'll just let you know down the road, the second half of the class, we do this all backwards. We start with the derivative and we go back to what we started, and that's the whole class. So what you're learning now is going to be helpful for you. So if you get good techniques down for going from the function to the derivative, all you got to do is flip it, and you got the second half of the class in your pocket. Okay. Almost. There's a few tricky things too, but that's pretty much it. As we go forward, and then the second half of the class we go backwards. We start with the function and we go backwards. Because sometimes we know the data, we know the values, and then we want to know how is it going to change in the future. Sometimes we're recording rates of change, like speeds. If we have those, we have rates of change, and what we want to do is go back to where what the values are. We know how fast our profit is changing, but we want to know what our profit is. So that's the second part of the class. Okay, so let's just do some algebra to clean this up now, because we're almost done here. So this x to the 0 is just 1, right? So 1 times 2/3 is just 2/3, a constant. This one we're going to rewrite as plus. We're going to put the 6 in the numerator. we're going to move the x to the negative 2 down to the denominator and put it as x squared. Okay, and then we come back, oh yeah, that's what happened there. This one now we got to multiply 0.2 times 2/3. And there's no easy way to do this because 2/3 is not a very nice fraction. It's 0.66666. And if we multiply by 0.2, we get 2 times 0.2 is...
Wouldn't it do 1/5 equals to 1/5?
Yeah, you could do that. I think that's the easiest way. And here's the question. The thing is that some of you recognize in the homework, you can put in a decimal, and if you don't have enough decimal places, sometimes they want the fraction. So yeah, you could do 2/3, and then 0.2 is also a fraction. It's 1/5. So you could make this into 2/15. Or you could take 2 times 0.2 over 3. 0.2 times 2 will be 0.4. Do I get the decimal place right, I think? So I think this will be 0.4 over 3. But that's cumbersome to have a decimal and a fraction together. I'll go ahead and just do the 2/15. I don't think we get to ones that are... Again, you could also put in your calculator and whatever decimal it is, I think you'll be fine. The other thing is, remember, when I do score the homework, what I'm interested in is that you're getting some practice and you're understanding how to do these things. The technicality of this, should this be 2/15 or should it be 0.4 over 3, or should it be some, you take the decimals and multiply them out and it's marking it wrong, but you've got basically a correct answer. That's why I go through, and as long as you've got 90%, I'm going to give you 105%. However, if we're getting enough of these, and you're not getting 90%, you can always appeal. And so once I post grades and stuff, again, if you feel, hey, I think I was marked down on a lot of them, but we'll talk about them then rather than as we go, because trying to, so just do your best, but focus on learning the content and go. And then again, we've got x to the minus 1.2, so I'll put it down here as a positive 1.2. And then at the end, that's the easy part. There's nothing to do to it. Just leave it as it is, and that's our derivative function. So again, and sometimes I choose some of the more complicated ones rather than doing, so this has a little bit of everything that you might see. Yes?
Where is this intersecting on the graph? Wouldn't there be like the derivative, the whole graph being what point you pick?
Yes, so what this is it allows us now to pick any point on the graph, and if we plugged up, so if I pick in, say, x equals to 5, if I plug it up here, I can get f of 5. I will get its function value at that place. If I plug it in down here, I'm going to get the rate of change. I'm going to get the slope of the tangent line at 5. And so yes, so this is where the tangent line is kind of changing. If you were to kind of, yeah. Now I have complete control over it. I can plug in any number I want for either one of these. But just remember, when I'm plugging into the derivative, I'm getting the slope of the tangent line. So yes, it's different, and it's one of the hardest things to pick up. I mean, I don't have it real intuitive between the two. I have to think about it. There's one is the function value, one's the slope, and I've got colleagues that are real smooth at it, but they have a harder time teaching it because to them it just makes sense. I think I'm a good teacher because nothing makes sense to me. So I'm always trying to talk you through and make sense out of it. Okay. So again, this is more of a review. We can take the derivative if we've got x, some number times x. Remember, the x just disappears. It doesn't really disappear because it's x to the 1. 1 minus 1 is x to the 0. X to the 0 is 1. So whenever you have just x, again, it seems like just x, but x to the first power, when you take its derivative, all that's left is the coefficient, the number in front. when you take a derivative of a number, no variable, just a number, you always get 0 because remember, a function that's a constant is a horizontal line. It has a slope of 0. So that's where that comes from. Again, here's some examples. So derivative of 6x is just 6. It's a number 6 because then it becomes x to the 0. Derivative of a number 5 is going to be 0. Okay, because that's a horizontal line. So those are two simple rules, but again, they're also ones that seem to cause some of the most problems because they just do. So let's look at an application, and this was taken from a homework problem. I don't know if it's in this homework because again the coordinators kind of update what they assign, but this was an assigned homework at one point. So a stone is thrown down at 104 feet per second from a height of 1,200 feet. The good news is we don't have to calculate that, but we sort of see it in the function here. So we see the 1,200, that's where it started. The 104, that's its power, and then this minus 16t squared, that's actually the power, the force of gravity pulling it down. We don't really need to know that because it just wants us to compute the derivative. So what we're going to do is we'll take the derivative piece by piece. So what's the derivative of 1,200? 0, because it's a number, it's got no variable. I'm going to write it down as 0 just to show that I took its derivative. So 1,200, its derivative is 0. Then I've got minus 104t. Think of it as x, whatever. So if I take that derivative, what do I have? Just 104. If you want to think of it, it's x to the 0 power. The 1 came down, multiplied, didn't change anything, x to the 0 power. I'll put it here just to, but then we'll take a step to clean it up. It could just put down negative 104. No problems. And then when I take the derivative of the last term, negative 16t squared, what happens? Actually, sometimes in the homework they'll use t and they want the answer to be t, and if you put an x it marks it wrong, so I better use better form here. Since they're using t, I'll use t. What's our derivative of negative 16t squared? 16 times 2 is 32. Subtract 1 from 2. 2 minus 1 is 1. And so our final answer, we don't have to write the 0. We don't have to write the t to the 0. So it's just minus 104 minus 32t. And what we're going to see is this is giving the height. So it's a position function. What we'll see, and we don't do it as in the engineering based one, we talk about this a little bit more, but when we take the derivative, remember this is its location. The derivative of the location function, remember it's a rate of change. It's how the position is changing with time. This is speed. What we have is speed. So the first derivative is, if you've got a moving particle, a rock, it's moving, you've got a function that will tell you where it is. That's the first function. The derivative of that function tells you how fast it's changing its direction, what its speed is. And then now, see, it's a lot easier. We don't have to do limit calculations for each of these points. We just plug in 0 to this function, right? Or you use it in your graphing calculator, you can actually put this function in there. In fact, I did do one thing today. I did more than one thing, but I did get my subscription to the TI calculator. So let me what are we doing? Yeah, we're okay. Here it is. I got this updated. So I'm gonna, And again, not that you have to have this calculator, but it's, how many of you have a TI-84 or 83? Few of you. They gave me a subscription. Let's see if I can, so I don't have to sign in every time. Let's see if it'll let me just use it. Not I can go to the other one, but I just, at this point, we just have to put the function in because we've got the derivative. Okay, here we go. So I'll go to y equals, and let's clear this out. What was our function? It was minus 104 minus 32x. Okay, so that's our derivative function we came up with. What I want to do now is I want to go to the table, and it's got all my values. So at time 0, it's going 104 feet per second. That's exactly what it told us, right? At time 1, at 1 second, it's going negative 136. But notice all I have to do is now copy over my answers. I've got all these, but I remember these are rates, right? These are speeds. These are not location. It started 1,200 feet. So this, if I wanted both, I could do both. So I could put in the original function here, but now I've got the derivative, and I can, just from this table of values, I can get that. I can also look at the graph. I see what that function looks like. Obviously, it's very negative, so I'm going to have to maybe come out. But this is the derivative function. So what I now have is also a way to compare what a derivative function looks like in comparison to the original function, right? I could graph both of those. The original function was 1,200 minus 104, oops, x minus 16 x squared. I'm going to see if I can get a good window on this. Let's go from, we're going to start at time 0. We're going to go for 10 seconds. It's probably far enough. We're starting at 1,200 feet as far as the distance where we're at, so let's go 1,300. And then we know that the rates are getting pretty negative, so let's go maybe negative 400. And I'm going to look at that graph. And we see that here's the graph of the rock. So this is actual sort of thinking of the height of the rock at various times. It's not necessarily the path of the rock, but it's the height of the rock. So the rock is coming down. We see the slope which is what this is, right? So the function for the graph for the rock's position was quadratic, right? It was minus 16x squared. The graph for the speed of the rock is linear, right? Because we subtract 1 from the exponent. So we see those two things here, but now as we're able to take, again, the part of this activity, this section is to just take the derivative. But what I want you to see is as we're going to quickly get into using it for applications, we're actually now able to also graph both the original value function and the derivative function on the same thing to kind of see how they look. And what you see is if we see a vertex, now remember these values on the blue line, those are actually slopes of the tangent line. So the slope of the tangent line at various places, if we saw a slope here, it would be going, again, so this blue line is not the tangent line, it's the values of those slopes of the tangent lines that go along here. And I think that's it. So we could fill in that table, we could do that one, and we could answer now, when does a stone reach the ground? Again, we could look at that from the graph, so we could do that with algebra. And then how fast is it going when it hits the ground? Again, we can see it hits the ground here at 1, 2, 3, 4, 5, 6 seconds. So we could then find the value at 6 seconds, right? So there is a function here. If I go second calc, I can actually go to the value. I'm not sure which function I'm on, but let me put in 6. And if I'm on the right function, I was on this function if I was on that. So the value at 6 is negative 296. So it was going 296 feet per second when it hit the ground. Probably put a little pothole in there or something. Hopefully it didn't hit somebody on the head, because that wouldn't feel too good, right? But so we can now find this. If I went to the function at 6, and let's see, I think I can do that if I go up here. Notice at 6 seconds, its position is 0. It's hit the ground. But its speed, its rate of change was, and the negative means it was going down instead of up. It's coming down at 296 feet per second. Okay, so that's what we're going to be able to do, is we're going to be able to connect these two things. And again, with business, it may be cost functions or profit functions, but we'll also be able to connect that with its derivative of how it's changing. Okay, because now we can actually manipulate the function directly. We don't have to go through limits anymore. So that's what I was telling you. Don't worry too much about limits. We're going to learn something better, and then we're going to just stop using them. The limits were just a tool to get us here. I like to compare it to crossing a river. If you're in a boat, cross a river, a boat's a great thing. But you get to the other side, do you really want to carry that boat all over with you when you're hiking? I say leave it behind and let's do that. That's what we're going to do with limits. We crossed the river. We're now at a place where we've got these shortcuts. We're going to leave those limits pretty much behind us. Okay, and we're going to be fine. Excellent. Any questions? No questions? I think I closed out I think I did. Oh, that's still here. But we're pretty much done with that, because that's just a blank page in case I need more room. So you're welcome to hang out 15, 20 minutes. Again, if you had more questions, I'm happy to stay. When the next class comes in, we can go out front, but have good luck. Have a great weekend, actually, right? Oh, please don't come to class on Monday. The holiday. I'll try to remember myself, but none of us need to be here because it's all going to be locked up. So Monday's a holiday. We'll see you next Wednesday. Take care.